everyone. Welcome to yet another very exciting review session for the PE exam. Um, Today we have a lot of work to do. We are going to cover structural design, and what we cover today builds upon what we learned last week. So I hope that you have taken some time to study what we reviewed last week. Today, the material that I will cover addresses um, structural design topics in the morning exam. I will tell you some specific types of examples that I think you should spend time um, familiarizing yourself with. Uh, and also, those of you who are planning on taking the structures exam in the afternoon, I do have some sections designated to you which I may not go over in detail, but I will tell you that that's the part that you should, on your own, study for the afternoon structures exam. And also, those of you who may be taking the construction exam in the afternoon, many of the topics we covered today will also help you in the construction exam in the afternoon. Um, Specific topics that NCEES lists that we will cover today are the following: member design, loads, and codes. Specifically, I will go over design of concrete beams, very fundamental, elementary types of information that will be helpful for the exam. And towards the end of the presentation, I will also go over some examples of steel design, loads, and also member design, but specifically the kinds that you might see in the morning exam. All right, so let's start the session. But before I do that, I want everybody to please uh, write down the following terms. What I need for you to do is to write down a list of um, terms that I will share with you, and I want you to, throughout the presentation, I want you to make sure you learn how to do these things. All right? Now, the first one, cracking moment. Cracking moment. This relates to concrete. We're not talking about the time at which the concrete cracks, but we're talking about the load that causes a certain magnitude of moment that causes the first crack to occur. So that's called cracking moment. You may be asked to calculate the cracking moment for a given situation. All right? Number two, I want you to learn what we mean by modulus of rupture. This is for concrete, modulus of rupture, and learn how to calculate it. Number three, nominal moment. I will show you a very straightforward method to calculate the nominal moment for a given concrete cross-section. Then I would like for you to learn what we mean by beta 1. It's an index, beta 1. We'll go over all of these things. And then the fifth item is the ultimate moment capacity. So that's the ultimate moment capacity of a concrete section. Adam, no. Okay, so let's move on to the next slide. And as I said, we are going to have a lot of fun together. The level of material is a bit higher theoretically than we have covered last week. But again, we're just getting more sophisticated day by day. All right. This stress-strain diagram is something that I covered last Thursday, so I'm not going to go over it in detail. However, I will show you one thing. By the way, this is a stress-strain diagram that's typical of a certain class of um, materials that we cover, that we call ductile materials. I want everybody to make a note of that. Ductile materials. All right. So ductile materials um, exhibit a stress-strain relationship as depicted by this curve. And obviously, I say steel. So steel is an example of a ductile material. So who can tell me what a ductile material is? And then the next topic that we will cover is uh, slide 3, brittle materials. We have brittle materials, and brittle materials actually have um, a stress-strain diagram such as the one that I'm showing. All right? Okay. Well, let's talk about brittle materials versus ductile materials. I will not spend too much time on it, but I will tell you, an example of a brittle material is concrete. Um, and I will start with brittle materials. These are kinds of materials that um, they fail without any warning. They give us um, no initial warning before they actually fail. So think about, well, concrete, for example, that's a brittle material. Give me another example of a brittle material, something that's actually we use all the time. Yeah, glass. Uh, Ryan Allen says glass. So glass is ceramics too, but glass is a very good example of a brittle material. Chalk is a good material. Cast iron, yes. All right. So these are materials that fail without giving us any warning. However, I'm going back to slide number 2. Ductile materials give us some warning before they fail. And steel is certain carbon content steel certainly are ductile materials. So what do we mean by not giving us any warning, or in this case of the ductile material, giving us some warning before they fail? Well, what happens is this. Um, Ductile materials go through an appreciable change in dimension before they fail. All right, and it happens in that area that I've circled. All right, so ductile materials give us some warning because they go through an appreciable movement, change in shape before they actually fail, and that is what we refer to as ductility. All right, so ductile materials that have this kind of typical stress-strain curve, what we know about them is the fact that the initial part of the stress-strain curve is linear. Remember, guys, we talked about that last week. You see that red line? That is the segment of the stress-strain curve below the proportional limit. That means, well, from the lecture last week, we know that that segment of the stress-strain curve is indeed linear, meaning it has a constant slope. And what did we call that constant slope? Yes, absolutely. Ian says that constant slope is the modulus of elasticity. All right, so that's the modulus of elasticity of the material. So with ductile materials, we can just calculate the modulus of elasticity by calculating the slope in the linear region. However, when we talk about brittle materials, specifically, let's talk about concrete. Look at the curve. There is no uh, recognizable double kink, so we don't really know exactly where the yield strength is. But something else, there is no segment that is linear in this stress-strain curve. So how do we calculate the modulus of elasticity? Well, this is slide number 4, shows some examples of how we go about identifying the modulus of elasticity for a brittle material. There is no one single modulus of elasticity. There are several methods. One is called the initial tangent modulus. The other one is the secant modulus, chord modulus, or tangent modulus. Now, let's move on to the next slide. Here, I have given you a stress-strain curve. This is an actual stress-strain curve for a specific concrete with the water-cement ratio as specified here. The compressive strength of it is 3,000 psi. And what they're asking here is, well, could you tell me, please, the value of the secant modulus, chord modulus, or the tangent modulus? I'm not going to go over the specifics of these calculations. I'll leave that up to you. So please take a look at it, and I will tell you, all of these calculations are based on the numbers that I have identified from the stress-strain curve. All right, so take a look at it, compare this with the previous slide, and see if you can produce the numbers and follow the solutions. The solution is on the right-hand side of this page. However, we have more exciting things to do together here, so let's take a look at slide number 6. We are talking about concrete, and you may know, many of you probably know, that concrete, a structural designer, she can design the concrete mixture so it would produce a concrete with different compressive strengths. All right? And the very bottom curve, this is a family of curves, but let's take a look. The nomenclature is very important because we're going to repeat these terms throughout the presentation today. So when you can see, it says F prime C is equal to 1. The 1 has the unit of KSI, keps per square inch. All right? So 1 keps per square inch is equal to 1,000 psi. And F prime C designates the compressive strength of that concrete. So that mixture that was used to produce the concrete with the stress-strain curve at the, with the very bottom curve, that gives us a compressive strength of 1,000 psi, and by definition, and this is the standard, the compressive strength of 1,000 psi is supposed to be reached, it's designed such that it is reached in 28 days. 28 days after the mix has been placed. All right, so if the compressive strength is 1,000 psi, you get the very bottom curve, and then if you increase it to 2,000 psi, you get the second curve. F prime C equals to 3,000 psi is 3, and all the way up to the very top curve relates to a compressive strength of 6,000 psi in 28 days. All right, now I need for you to make certain, well, help me make some observations from this series of curves. And guys, what we're talking about right now, all of these principles that I'm introducing to you, we will be using in the subsequent problems. All right? So tell me, what if I give you this series of curves and I ask you to please make some observations? What are some of the observations that you could make? Um, okay. All right. Excellent. Um, Several of you are making some predictions here. Stephen says um, when the stress, the highest stress, the highest stress occurs where the strain is 0.002. And Ryan says the same thing in a different way. Strain peaks around 0.002. So when well, actually stress peaks where strain is 0.002. That's excellent. So let's summarize that. So with this family of curves, and this is true with all concretes basically, when the strain is 0.002, we assume that the concrete achieves its highest stress. All right. Now, what else? What else can we tell me? What can you tell me about 0.003? And remember, the x component here is strain. All right, strain. An axial strain last week we defined as delta L over L. So when strain is 0.003, what observation would you make? Okay. Um, Steven says rupture occurs, and Donald says the same thing. Yes, Helen says failure. That's correct, and Ian says well, 0.003 strain is when we assume that failure occurs. That's basically what many of you have been saying. Now, let's see if you agree with that. Basically, if you draw a line like this, we're saying when strain is 0.003, concrete ruptures. Well, guys, that is true, certainly true when for the top two curves, when 6,000 psi and 5,000 psi. Because think about it, right in this region, that's where the concrete, the curve stops and the concrete fails. That is not so true with the 3,000, 4,000, 1,000, and 2,000 psi concrete. However, I will tell you, it is a conservative assumption for those other concretes. Therefore, ACI, American Concrete Institute, makes that assumption in the design equations. All right. So we are going to use these principles we've talked about. We are going to assume concrete is going to fail when the strain reaches 0.003. Slide number 7 pretty much discusses and tells you what I just told you about the previous slide. So please read this. Now, here we're talking about the modulus of elasticity for concrete. Remember I told you earlier that because concrete is indeed a brittle material, it really doesn't have a linear portion. The stress-strain curve does not. So we have an option of 4 or 5 different ways of calculating the modulus of elasticity. However, for design purposes, ACI, again, American Concrete Institute, they specify and use the kind of modulus that I showed to you that's called tangent modulus. So they actually just use one in the design equations, and that is the slope of the tangent line drawn to the stress strain curve at the point where the stress is 0.5 F prime C. And again, F prime C is the design compressive strength. So at the zero point 0.5 times F prime C, on the curve, we draw a line that's tangent to the curve, and we calculate the slope of that line. You don't really need to actually calculate it because, uh, again, ACI uses this equation to give us that value. So this is what we need to do. What you need to do is please learn this equation here. E, modulus of elasticity for concrete, is equal to the following equation. 33 times the square root of F prime C times W to the power of 1.5. W, guys, you need to understand what W is. W is the unit weight. W is the unit weight of concrete. All right? So you substitute the unit weight of the concrete in that equation. You substitute the value of F prime C, design compressive strength, in that equation, and this will give you the modulus of elasticity for that particular concrete. All right? Now, this equation applies for concretes that have unit weight somewhere between 90 PCF. That's pounds per cubic feet. So 90 to 155 pounds per cubic feet. All right? Now, most concretes have a normal standard concrete. We call it normal weight concrete. Has a compressive strength. I'm sorry, not the compressive strength. I meant to say unit weight. A normal weight concrete has a unit weight somewhere between 155 and 145 PCF. All right? So you need to write this down because there will be opportunities for you to use this. All right? Normal weight concrete has unit weight somewhere between 145 to 155 PCF, pounds per cubic feet. Now, assuming 145 PCF, ACI has come up with this equation here. So you substitute, or they substituted 145 for W in that top equation, and then they reduced it to this thing. And this equation you may have an opportunity to use on the test, all right? It's the modulus of elasticity is 57,000 times the square root of F prime C. So F prime C, compressive strength, will be given to you. All you have to do is just substitute in this equation. You calculate the modulus of elasticity. All right. In just a few minutes, I'm going to bring all of these different topics that we are talking about, bringing it all together and show you how we can use it. Joseph, I think I told you what W is. If you still have a problem, let me know. Jeremy, no, unit weight of concrete. He's asking if the unit weight includes steel or not. No, it does not. That's the unit weight of the concrete itself. And Joseph says also sometimes gamma is used for unit weight. Yes, you're correct. W or gamma is used. That's for unit weight. But gamma is usually used for soil, and for concrete, customary to use W. All right. Laura is asking, is F prime C in PSI? I think it is in that equation. No, Tyler, no. Okay, now at this point, we're looking at slide number 9, and I want to tell you a story at this time. I want to tell you about the story of a typical concrete beam, the life of a typical concrete beam. And let's assume there is a concrete truck delivering concrete in its plastic form, flowable form into a job site, and then we actually deposit this concrete, let's say, into a form that would give the shape of a beam, a typical beam, let's say with a rectangular cross section. All right, just if you can imagine, it's a typical concrete beam. It could be part of a structure, a parking garage, or whatever that it is a member of. This concrete beam actually throughout its service life goes through 3 different stages. So there are 3 stages of life for this concrete beam, and I will tell you the story starting from the first day, first few hours of its life, and that stage is called uncracked. So when we actually place this plastic concrete, flowable concrete, in the form and it assumes its shape, well, we go through the process of curing the concrete, but we don't place loads on it. We very gradually start placing load on this beam. And the very first stage of its life is uncracked. There are no cracks anywhere in this beam. And finally, there comes a moment, and this is moment in terms of force moment, that the first crack occurs on the tension side of this beam. And that is the very first crack that is developed. That is the end of the first stage of the life of that concrete beam. It's no longer uncracked. And when that happens, the second stage of its life begins, and that we refer to as cracked elastic stage. So there are cracks within this beam on the tension side in general, but the behavior is elastic. So we call that cracked elastic. Then when it gets through that stage, then part C, the third stage, which is called ultimate strength stage, begins. Guys, for the purposes of this presentation today and what you need to worry about on the test, especially in the morning, we only need to consider the first 2 stages, and that is what we will be talking about today. So the uncracked stage and cracked elastic stage. Each one is governed by certain equations, and we will go over that. By the way, the uncracked stage could last anywhere from a few weeks to a few months, depending on the concrete mixture and the loading and the structure itself. All right? And then the second stage, cracked elastic stage, can last for many, many, many years. All right, let's move on. Here, remember early on I told you to please write down a series of terms, and throughout the presentation we're going to learn what they are and how to calculate it. Sure you remember. What was the first term? Yeah, just go back to the first page where you wrote it down. Yeah, cracking moment. That's right. That's right. I can just hear Helen said cracking moment. So it's cracking moment. And guys, I'm going to show you how to calculate this, because this is a rather simple concept, but it can be on the test. And basically, remember I told you the first stage is uncracked? Well, when the moment diagram, and this is the moment diagram, look at it. The moment diagram that I showed you last week, how to calculate it, for the values that are equal to the MCR, that's cracking moment. And anything higher than that, that region of the beam, it has cracks, all right? So one of these begins, and then the subsequent cracks develop also. These are all on the tension side. What are we talking about tension side? Tell me, this is a review of what I covered for you last week. This moment diagram that I'm showing you in part A, it's all positive, right? It's above the x-axis. So what did I tell you about positive moments? Positive moments cause the beam to behave how? You got it. It's a smiling. It's a smiling face. So positive moments cause the beam to deflect like this. So what do we learn? What do we observe? The bottom is in tension. All right? So the bottom is in tension. These cracks develop on the tension side. Very good. Now, on the test, they will give you certain properties, and they will ask you, please find the cracking moment for this beam. This slide actually shows the second and consequently the third stage of life of the beam. So let's move on. What I want you to concentrate on is this, how to calculate cracking moment. All right? How to calculate the cracking moment, and I'm going to show you an example. This is very important, and it's not difficult at all. All right? Okay. Now, guys, we are talking all about beams. And beams, we talked about it last week. It was what? Flexure, all right? So the flexure equation, what type of stress was associated with the flexure? You got it, bending stress, bending stress. And if you go back to the notes that I presented to you last Thursday, what equation did I give you for bending stress? I'll see if I can write it here. Do you remember the equation for bending stress? What I gave you last Thursday was sigma is equal to mc over I. Let's see if I can do this. And we spent some time explaining and learning what m, c, and I are in that equation. All right? Now, when it comes to concrete, we use the exact same equation, but with different nomenclature. All right? So here's what I want you to pay attention to. This equation at the very top right, is exactly the same as what we called last Thursday. Sigma is equal to mc over I. Except when it comes to concrete, we use the lowercase f for stress. All right? So that is stress. And what about the other ingredients? M is M. What we called C last week is now Y. Okay? And what the denominator, which was moment of inertia, is still I, moment of inertia, but this one has a subscript G. It's I sub G. G stands for gross in this case, and I will explain to you what that is in just a minute. All right? So the flexure formula in terms of concrete is F is equal to my over I sub over I, my over I. All right? Now, the other thing that I want you to really understand is, okay, if you go back to your notes, the second term I told you that you need to learn is modulus of rupture. If you go back to your notes, if you wrote it down, that's what you wrote down, modulus of rupture. Guys, this is where we're going to learn what modulus of rupture is, and more importantly, how do we calculate it? Well, in the middle of this slide that we are all looking at, you see this very small equation. F sub r, that stands for modulus of rupture. All right? Modulus of rupture. And basically, that is the stress. That is the stress. Now, pay attention. That is the stress that causes that first crack to occur on the tension side of the beam. All right? F, because it is a stress, and R, because it causes rupture. So, and we don't call it rupture stress. The concrete industry, the concrete professionals, they refer to it as the modulus of rupture. All right? So learn that. Modulus of rupture simply, very simply, is equal to 7.5, the number 7.5, times the square root of F prime C. All right? Now, in order to calculate the cracking, the moment that causes the first crack, M cracking down here, we just rework that Fletcher equation. There it is. M cracking is equal to FR I sub G, gross moment of inertia, divided by Y sub T. Now, why do we say Y sub T? T stands for tension. So Y is the distance between the centroid of that cross-section to the side that's in tension, either top or bottom. Let's move on to the next slide. Now, I want everyone to get involved in calculating the answer to this problem. All right? Just imagine this is the day of the test, and let's see how we can do. It says, for a concrete with a compressive strength of 4,000 psi. So F prime C, this concrete has been designed to reach 4,000 psi in 28 days. So F prime C is equal to 4,000 pounds per square inch. Then it says, assuming the concrete is uncracked. Please underline this and make a mental note. I will tell you what that means. If you see it on the test, exactly how do you deal with it? All right? They say concrete is uncracked. And then they say, would you please compute the bending stresses in the extreme fibers? That means either top or bottom. If the beam is subjected to a moment of 25 foot Keps. Make a note of the units, 25 foot Keps. All right? What is it that we are trying to solve for? Bending stress. So what is the equation? Let's go to the next slide. There it is. Do you agree? Okay, good. So this is the equation that we apply. It's concrete. So F, compressive, well, actually it's stress, flexural stress, is equal to my over I sub G. Now, let me tell you why the moment of inertia in this case we call I sub G. The G stands for gross, and not because it's yucky. We call it gross because, pay attention, we are using the entire cross-section, the entire concrete cross-section to calculate the moment of inertia that we call gross moment of inertia. And why? Where do we get the clue that we must use the gross moment of inertia? Because they specified this is uncracked. All right? Remember I told you the significance of the uncracked? I will tell you what the significance is. Here is the significance. All right? So, and Gary says when it is uncracked that you use the full section. Absolutely correct, yes. So it means in order to find the moment of inertia, I'm going to use, well, this is a rectangle. So the moment of inertia for a rectangle is 1/12. 1 over 12 times B times H cubed. And let me see if I can erase some of these things. I guess I cannot. I did it. So the moment of moment of inertia here, I is 112 times B is the base. All right, we have the base, which is 12. H, in this case, we are using 18, the entire depth. All right, and that's what we mean. This will be the gross. All right. Um, and you may ask, is there a case? Is there a time that we would not be using the entire cross section? Yes, absolutely. And I will tell you that in just a minute. Yeah, Patricia, I hope I pronounced that correctly, Patricia. Um, she points out that I did not give the dimensions on slide 13. You're correct. That is an oversight. They will give you the cross-section, the dimensions. And here it is. These are the dimensions for that should have been on slide 13. Okay? The dimensions, they will give that to you. There is another question about from Mary. Mary says, what about the dimensions, or I'm sorry, the units for F prime C? Is it PSI or KSI? Well, it could be either. It could be either. They will specify that, and all of us need to pay very close attention to what the problem actually specifies, because we need to deal with it. So it would be either pounds per square inch or keps per square inch. All right, and I will give you examples of that. Now, the second part of this problem, and by the way, to find the stress very quickly, look, guys, what do they use for? What do they use for Y? It's 9 inches. All right, 9 right here. All right, so that is the stress. And the other thing is the units were 25, uh, you see the moment. The bending moment was given to be 25 foot kips. And when you do the equation, please pay attention. This 12, this is a conversion factor. I multiplied the 25 by 12. Now it's inch keps, and then I multiply by another 1,000. Now it's inch foot, because this y is in inches, 9 inches, and the moment of inertia in the bottom, that is inch to the fourth. All right, so we made it compatible, so the answer comes out to be 463 psi. So pay close attention to those conversions. All right, now the second part, which is actually the more important part of this problem, this is very important. They ask you, and it's a very good possibility, they ask you, what is the cracking moment for this beam? Here's what we do. This is the equation for cracking moment. Make a note of it in the very bottom, and I showed you exactly how we got it on the previous slide, a couple of slides ago. All right? So we know I gross, we know YT. What we don't know is FR. And again, I will remind you, FR is the modulus of rupture. It is the stress that causes the first stress in the concrete beam. All right? It's the stress that causes the first crack. All right, the stress that causes the first crack in the concrete beam. So um, how do we calculate it? There it is. That's that simple equation that I showed you in the previous, I think, 2 slides ago. All right, make sure that you highlight that. So rupture, modulus of rupture is 7.5 times the square root of F prime C. In this case, F prime C is given to be 4,000. You substitute in the equation. By the way, guys, I think there is an issue here. I need everybody's attention. This is 4,000, not 4,000 times zero point 0.5. That's 4,000 to the power of zero point 0.5. Would you do me a favor and correct that? Yeah. So it's FR. The value is correct. It's just the equation. So it's 7.5 times the square root of 4,000. Please make a note of that. Yeah, and Donald says see the equation on page 12. All right. Uh, so when we do this, substitute all of this, the cracking moment comes out to be 25.6 foot kips. Does everybody follow? This is a very realistic problem. So Fahmy, Amjad asked me, where do you get the 9-inch? 9-inch, Fahmy, that's it's this distance. It is the distance from the centroid to the tension side, which is 18 divided by 2. All right? So when you find the cracking moment, this is the equation. And also, when you're, this is very important. Make a note to yourself. When you're calculating the cracking moment, you must use the gross moment of inertia. Use the entire section, all right? And use the entire depth, in this case, 18 inches. All right? Very good. Let's move on. We have a lot more exciting things to cover. Now, I hope that you're having fun. Here, Ryan says, so this beam will not crack as long as the stress is less than the cracking stress. Absolutely, yes. But once the stress reaches the cracking stress, then the first the first crack will occur. All right, but you're correct in what you said. All right, now you know we always talk about reinforced concrete. When we say reinforced concrete, what we're talking about is that we have a section of concrete and we reinforce it with steel. Now, why do we do that? We do it for the following reason. Think about it. Concrete is a very, very strong material in compression. All right? When concrete is placed in compression, it can withstand large stresses and carry large loads. But concrete is rather weak in tension. Now, when we talk about steel, steel is the opposite. Steel is very, very strong in tension, however, not so strong in compression. So what we do, we combine these two positive properties. So when we combine steel with concrete, it's the marriage of two materials that we get high compression resistance from the concrete part, and then we get high tension resistance from the steel that we use as reinforcing. However, and guys, please pay attention to the next thing I'm telling you. For that steel to really be helpful to us, we need to place it, where do you think? You got it, on the tension side of the concrete. All right? So here's what we need to do. We need to look at the beam, you look at the dimension, and you decide where is top or bottom, right or left, which section of this concrete element is going to be in tension, and that is where you need to place the steel. This concept that I just told you is tested on the exam over and over again. And specifically, I will tell you, in a little bit, I will tell you how they test that knowledge on the test. All right? But this, what I just told you, is very important. Now, this the reinforcing bars come in different sizes. And there are tables. I don't have a table included in the handout here, but there are tables that you can actually refer to, and different size reinforcing bars are identified by their sizes. All right, and they just designate a number. For example, number 3. Number 3 is the smaller uh, bar, the smallest bar that we use here in this country, and it goes all the way to number 18. Now, there may be special occasions where you have used, some of you who are structural engineers may have used some size outside of this. But the standard size reinforcing bars are number 3 all the way to number 18. All right, so we designate them by numbers. Now, in the calculations that we are doing, the kind of calculations we're doing today, we need to know the diameter, we need to know the area of each bar. And as a rule, up to number 8, the bar diameter is in eighths. What that means is, for example, a number 8 bar has what bar diameter? 8 times 1/8. So you're right. The diameter of a number 8 bar is 1 inch. All right. Number 7 bar, the diameter would be 7/8, and so on. Now, also, just for your information, I recommend you use a table for this, but the area of a number 9 is equal to a corresponding square of 1 by 1. Number 9 has an area that's equal to a square of 1 by 1. So what's the area of a number 9 bar? 1 square inch. All right? And number 10 corresponds, the area of a number 10 corresponds to area of a 1 and 1/8 square, and number 11 has this correspondence. All right? I want everybody to do this problem with me, please. This is also very important. So, if you go back to your notes, the third item that I said that you need to learn is nominal moment. What I said was nominal moment, and here I'm going to show you how to calculate the nominal moment for a given concrete cross-section. All right? You know, even though we call this structural design, but on the test, it will be very difficult for them to give you a true design problem. Those of you who are structural designers, you do agree with me that design is an open-ended problem. And it has multiple correct answers. However, on the test, because the nature of the exam is multiple choice, they cannot give you a true design problem. So what they will give you is the kind of problems we're doing here. It's design in the context of analysis. All right. So it's a design concept, but in order for it to have one single answer, it's really the analysis part of a design process. So here we are asked to find the nominal moment, and let's do it. It's not a difficult concept. It may take me a few minutes to go through these preliminaries, but everything I say is important and will contribute to what you need to do to get the answer. But hopefully when it's done, you will agree with me it's not a very difficult concept. All right, so let's say that you're given this cross-section with the dimensions that are given here on the left-hand side. And please note that they say these, oh, by the way, these round things here, those are the reinforcing bars. These are the reinforcing bars, and in this case, we are assuming that the tension is at the bottom. Don't always assume that the tension is in the bottom. In this case, we're saying that the tension is in the bottom, and uh, we have used 3 reinforcing bars. Each one is a number 9. And if you go back to the previous slide, I showed you number 9. The cross-section of a number 9 is 1 square inch. Therefore, the total area of the steel, A sub S, the total area of the steel is 3 square inches. I hope that you understand that because this shows up in several of the problems we'll be doing today. All right, let's see what we are given. Let's go back to the top of this problem. This says Fy is 60,000 psi. Please make a note of that. That is the yield stress of the steel. All right? When they say Fy, that's the yield stress of the steel that's used in this section. So that's 60,000 psi. And then the compressive strength of the concrete is given to be 3,000 psi. F prime C is 3,000 psi. All right. Now, what you see here at the right-hand side, learn it. Because for problems like this, the first thing you need to do is sketch that. All right? And basically, that is the stress distribution on this concrete beam. And what I want you to learn here is that every time you have a problem like this, just draw this line, the line as depicted. This is going to be, let me try to use a red line. Okay, we're going to draw this line. This is what you have to do, all right? But please note, this line does not go all the way to the bottom. This is a very important concept. This line goes from the top to where the steel is located, all right? The next thing you need to do is to draw these arrows here. That is on the compression side, all right? That's on the compression side. And those are stresses. And that stress is equal to, always is equal to 0.85 times F prime C. So this is always what I want you to do, is the first thing that you do. You draw that thick red line, stop at the center line of where the steel is located. The next thing I want you to do is draw these stresses here, all right? And we are showing it acting or pushing on the cross section because that's in compression. All right. Now each one of them, these stress lines, is the magnitude is 0.85 times F prime C. 0.85 times F prime C. All right. Now the other thing I want you to do is identify this dimension as small a, lowercase a. Now, so far, so good. The next thing I want you to do, and I will mention one other thing, and then we're going to move to the next slide. The next thing I want you to do is to identify the maximum force. These are forces, not stress, but forces. The top force is a compressive force acting on the concrete section. The bottom is labeled T, all right? T, which is for tension, and that's the force in the steel, All right, now, let's take a look. What I want you to concentrate on is this segment C. All right, this part C. Assume the variations. Now, I'm going to do this rather quickly, so I need your attention, please. Stephen, the answer is no. No. So here we have the stresses. 0.85 F prime C are the stresses. But I need everybody's help here. Guys, if I give you the stress and I ask you to please find the maximum force, I give you the stress and I ask you to find the force associated with it, what would you do? Critical thinking. What would you do? You know, last Thursday, I started the presentation by giving you an equation that helped us find the stress. Given the force, how did we find the stress? The very first equation was an axial stress. Those of you who said sigma is equal to P over A, you are correct. Stress was load divided by the area. Now, let's think about that equation. If I give you the stress and ask you to please find the load that's associated with that, what would you do? You got it. Multiply by the area. All right? So Gary says you multiply by the cross-section. And Joseph O'Donnell also is giving me the correct answer. So here's what we are going to do. And I hope that you're still with me on this. 0.85 F prime C is the stress. So we're going to take that and multiply by the area over which it's acting. All right? So take that stress and multiply by the area that it's acting on. Now, that area is equal to, what do you think? Well, that area is going to be equal to, this beam is like this. All right? And the cross-section that we're talking about, this stress is acting on, is like this shaded red. All right? Now, what is this dimension? Yeah, that dimension is equal to a lowercase a. All right? And what about the other dimension of that cross-section that this is acting on? You got it, b, which is the width of the beam. All right? So the bottom line is this. The area over which this stress acts is a, lowercase a times b. So there it is. The total compressive force is equal to 0.85 F prime C, that's the stress, times the area over which it's acting, which I just showed you what that area is. So that is A times B. Guys, this is the second or third step that you do because that's always the same. So big C, capital C, is the total compressive force, and it's equal to 0.85 F prime C times A times B. All right? Now, this A, we really don't know what that is. We have to calculate the value of A. And it's called the depth of the stress block. The depth of the stress block. Now, one other thing that we need to identify before we move on, and that is the total force on the tension side. On the tension side, I explained to you, that would be where the steel is. All right? So, the stress that's acting on the steel is F sub Y. Fy, that's the yield stress of the steel that we're using. So we take that value, that will be given to you. You take that and you multiply by the area over which it's acting. Now here, the area that we consider is only the area of the steel, which is A sub S. So there it is. Let's go to the all the way to the right-hand side of this page, and there it is, total force. The total force in tension that we gain from the steel is simply equal to A sub S, the total area of the steel, times the yield stress of the steel. Now, I'm going to ask you something very fundamental. If we have, this goes back to statics. If we have two forces, that are equal, but they act opposite to each other, what is it called? Because that's one, the other one is here. So the total compressive force and the total tensile force, big C and big T, those, by the way, they have to be equal for equilibrium. So if they're equal and each one is acting in a different direction, what is that called? Kenneth says it's a couple. Caleb says couple. Lisa says couple. Donald says a couple. Yeah. So here we have a couple system. All right. Now tell me, what is the moment that's produced? A couple system, actually, a couple force system causes a moment. All right. Now, that moment, guys, that moment is called nominal moment. All right. So here's what I want you to understand. Remember, I told you you need to learn how to calculate the nominal moment acting on a concrete section. There it is. What we call nominal moment, guys, is nothing other than the moment that this couple system causes. And I just told you how you can identify the magnitude of those couple forces. All right? Now, the next thing I will ask you is, how do we, once we have a coupled system, how do we calculate its corresponding moment, the moment they cause? Well, we just take one of the forces, because the forces are equal. You take one of them and the magnitude of one and multiply by the distance between the two, multiply by the moment arm. The distance between the two forces in this case is D minus A over 2. A over 2, that A is this thing, the depth of the stress block. D is important because I'm going to explain to you what D is. D is this distance from the top to where the steel is. All right? That's very important. Now, this slide 18. Now, everything I said to you, we're going to put that in practice. We're going to do an actual problem, and you're going to help me with it. But this slide 18 basically goes through what I explained to you and also tells you the process, what we need to do in order to find the magnitude of that nominal moment. What I like to do is go through an example with you. All right? So tag this page 19 because I'll ask you to go back to it and take a look at it. But before we do an example, very quickly, do you remember, well, the fourth item on your list, when I said the following lists of items you need to learn, number 4 was what I called a beta 1 index. Beta 1, actually, if you don't mind, I'm going to go back to slide number 17, and let me see if I can get rid of some of these red lines. All right. Well, I got rid of some of it. Okay. Here's what I want you to take a look at, please. This A. Lowercase a is equal to beta 1 times C. All right? Now, C is this distance. This is the distance from the top to the centroid. lowercase a is not the distance to the centroid. It is related to it, but it's not the distance. A is equal to beta 1 times c. All right, now I'm going to go forward. Here, slide number 20, it tells us what beta 1 is. And guys, sometimes they ask you this question, what is beta 1 for a given concrete? All right? So, and it's very simple. If you don't know it, you can sit there for the entire day and not know what they're talking about. But it's very simple. Beta 1 simply is a constant, and it's constant for a given compressive strength of concrete. So beta 1 prescribed by ACI code is equal to 0.85 as long as the compressive strength of the concrete is less than 4,000 psi. So the question would be the following. The compressive strength of a concrete is 3,000 psi. What is the beta 1 value for that? 3,000 psi certainly is less than 4,000, so there it is. Beta 1 is 0.85. If it is 4,000 psi, beta 1 is 0.85. However, for concretes that have a compressive strength higher than 4,000 psi, then you can use this equation to calculate the corresponding beta 1, or I just will explain to you in words. Beta 1 reduces 0.05, beta 1 reduces 0.05 for every 1,000 psi of increase. So pay attention. If beta 1 is 0.85 for 4,000 psi, so tell me, what is beta 1 for a 5,000 psi concrete? Well, that's 1,000 increase in compressive strength, so beta 1 will be reduced 0.05. So what would the answer be? 0.8. 0.80 if compressive strength is 5,000. Now, look at, this is very important, the very last line in the bottom of this page. It says beta 1 shall be greater or equal to 0.65. Well, when you read that, that is code talk. Those of you who are structural designers, you're probably familiar with that kind of language. But in simple words, what we're saying is beta 1, you can increase the compressive strength of concrete as much as you want, but there's a ceiling, there's a limit to how low beta 1 can go, and that is 0.65. All right. So anyway, for concrete of 5,000 psi, you reduce the beta 1 0.05, and it becomes 0.8 for a 5,000 psi. And what is it for a 6,000 psi? 475, correct. All right, very good. Let's move on. This goes back to that problem 2. Problem statement was given. You can go back. Helen, tell me, what slide number was it where we stated the problem? I think FY, the steel yield of steel, was 60,000. And here's what we need to do, actually. Step by step. Once you have the value, you have this sketch, we're going to calculate the value of T and value of C. These are the loads, all right? So T, the total load on the tension side, is AS times FY, this thing here. AS times FY. In this case, it comes out to be 180. This K, by the way, please just go ahead and write KEPS. That's that is 180 kips. Um, then we calculate C, capital C, the total compressive force. And I told you it's 0.85 F prime C times AB. Substitute. 0.85 is 0.85. This 3, it was given to be 3,000 PSI. We're using the loads in keps here. Lowercase a, we do not know what that is. This is the way to calculate it. And where do we get 14? Make a note of it. 14 is the width of that beam. All right, so capital C, that comes out to be 35.7 A. A is an unknown. Big T is 180. These two forces are equal. So on page 22, I am reiterating that T has to be equal to C for equilibrium. Therefore, 180 is equal to 35.7 times A, and there it is. We calculate A. Guys, this is the only way that we can calculate that, the value of A. And what is A again? The depth of the square block. Is everyone with me so far? Let's continue. The next thing that we want to do, remember, we are trying to find the nominal moment. And the nominal moment is nothing other than the moment that this force couple creates. So, we need to know the distance. What is the distance between the two force couples? Always, always, it's equal to D minus A over 2. And this is why it's important that we calculate the value of A. And I just showed you how we can calculate the value of A. Substitute it in here, D minus A over 2. The other thing that I've told you, but I want to make mention of it again, D is the distance from the compression side, the top side, to where the bar is, reinforcing, the center of the reinforcing bar. All right? So that's D. That's why we're using 21. Once we get that moment arm, then it's easy to calculate the nominal moment. Nominal moment would be equal to either the large T or the large C, because they're equal, multiplied by the moment arm. Please pay attention. It comes out to be in terms of inch keps, because those are the units we've been using, and then you can make a conversion factor and come up with foot keps. Now, you may ask, do I need to just leave it in terms of inch keps? Do I need to convert it to foot keps, or what do I do? Well, the answer is, look at the answers that they have, and look at the units that they use in their answers, and that is the units that your answers need to be related to. Okay. Here is a problem. It's a cross-section of a beam. Let's do this problem together. It says there are 3 number 8 bars. 3 number 8 bars. So either calculate the area of a number 8 bar or look it up in a table. A sub S, total area of the steel, is 2.37 inches. The width is given to be 14 inches. The overall depth is 24 inches. Remember, you only use that if it is uncracked. You only use that if you are finding the gross area. However, D, which is important, is given to be 21 inches. And once again, that's measured from the compression side to where the steel is located. Now, what you see here, this is a strain diagram. Well, I will not spend too much time on it, but I will explain to you what that shows. That shows That shows the strain at different locations. And by the way, one thing that I want you to do so you will understand this relationship, that actually the 0.003 should be here. 0.003 is um, what happens at the top of the concrete, and then this side here, this line should be located where the steel is. All right. So basically, that triangle would be down here. But what this is showing is the relationship between the strains. And do you remember we talked about 0.003? The significance of the 0.003 was that we assumed, or ACI assumes, if the strain in concrete reaches 0.003, we have reached failure. All right? Or I shouldn't say failure. It reaches the ultimate value that we allow it to reach. All right? Now, if the strain in the concrete is 0.003, then the strain at the steel level would be this. Just note that equation. And we use that, we identified it using uh, similar triangles. All right? All right. Let's do this problem together. For problem number 3, the one we just looked at, the previous slide, keep those dimensions in front of you. It says determine the value of A. Again, what is A? Guys, I know you may be tired, and what we were talking about may not seem that exciting to you, but I need your attention for another 40 minutes, okay? So we've got some time to go. Let's see. I want everybody to calculate this. The solution is given to you, but let's see if we can do it. Determine values of A. We need to find A. Then find C, and then epsilon T, that equation that I just showed to you. Now, 60,000 psi is the yield stress of the steel, and 3,000 psi is F prime C, compressive strength. The equations that I've shown you, what do? Well, you draw that sketch. The stress is 0.85 F prime C. Draw the stress block. Calculate big C, which is the compressive force. Write it down. It's always the same. 0.85 times F prime C times little a times little b. B is the width. Next thing, T, big T. What is that? Always is equal to AS, total area of the steel, times FY, yield of the steel. The next thing that you do, big C, set it equal to big T. And that, guys, is exactly what I have here. If you set those two equal to each other, A is the unknown you calculated. All right? So A is 3.98. If you don't get that value, please go back and refer to this problem and do it later. All right? So small a, depth of the stress block, as Donald says, is 3.98. Now, what's beta 1 for this case? Beta 1, remember, by definition, 0.85 if the concrete is less than 4,000 psi. So in this case, it's 3,000, so beta 1 is 0.85. Now, remember, We calculated A, but the problem says, can you find C? C is the distance between the top to the centroid. There it is. Remember, A, small a, is equal to C times beta 1. So if you know what A is, you can simply find C. There it is. Then, if we calculate the epsilon in the steel, that is the equation that I showed you on 2 slides ago. I told you we identified it using um, similar triangles. So epsilon t is the strain in the steel. You may ask me, why are we concerned about the strain in the steel? Well, there's a very important point here, and it's a very interesting point. So let me ask you, if you were the designer, I want every one of you to think about this. If you were the designer of this concrete section, would you want, if it reaches actual failure, hopefully it won't, but if it does, would you want the concrete section to fail first, or would you want the steel to fail first? Think about it. And Arash, I'm not sure exactly what you're asking me. I know what you're saying, but Arash is saying he would prefer the steel to fail first. Then Kenneth says no. He wants concrete to first fail. Christopher says we want to make sure the steel reinforcing yields before concrete fails. All right, guys. Ryan says we want steel to fail because it will yield and give us warning before it fails. And that is, all of you, most of you said it correctly, those of you who said steel, all right? And Ryan also offered the answer in a very simple way. So I want everybody to pay attention. When we design a reinforced concrete section, we want to force the section, dimension it such that steel will fail first. And that is because I told you before the difference between ductile materials and brittle materials. Steel is a ductile material, so if that reaches its yield stress, then it will give us some warning before it fails. If concrete fails first, it's a brittle failure and will give us no warning. All right? So, yeah, Mary Hill says if the steel is hidden in a concrete wall and it fails, um, how would that help us? Well, think about it, Mary. If if the steel is inside a concrete wall, but it reaches yield, it is going to go through some appreciable change in dimension and deformation. And that deformation will cause spalling of the concrete. And if you're occupying that building, if you're in a room where the wall starts moving because of a major sag, as Donald is mentioning, then you know there's something going on, and you're not going to stand around to see what happens. You get out of the building. Now, the building we will not save, but the people using the building we save, and that's the issue of ductility. All right, so that's why the designers would like to have ductility in their design. So how does this connect to what we're doing? Well, what we're going to do is, in order to decide whether the steel fails or the concrete fails first, we need to know the strain that's produced in each, either in concrete or steel, at the time that it fails. All right, we'll talk about that a little more later. But what about this problem? This last problem, I want everybody to please do this. What is the nominal moment capacity for the beam? The beam we've been just talking about, we found the strain in the concrete, we found the strain in the steel. Could you calculate the nominal moment? I'm going to give you a couple of minutes to do that. Go back and look at your notes, and see if you can calculate the nominal moment. All right. What do you think, guys? Caleb, what do you think? Jacqueline says 225 foot kips, and she's absolutely correct. Okay, so if you do this problem, you should come up with 225 foot kips, and here it is. Here's the answer. And just in case you didn't come up with that value, here's the answer. But if you didn't come up with that value, please go back and review it. It's very straightforward. Now, one other concept that I want to cover here in terms of moment capacity of concrete is, if you look at your notes, the next item, number 5, the terms that I said in the beginning you should learn, the 5th term was ultimate moment capacity. All right? So the ultimate moment capacity, we're going to cover that here. All right? Now, the ultimate moment capacity is the amount of moment that the designer would allow the structure or the element to be exposed to. What we covered before, what we called nominal moment is also called theoretical ultimate moment. So the theoretical ultimate moment is what the material in the cross-section can provide us. However, to bring in some factor of safety, the designers would like to reduce the exposure of the building to the amount of load. So instead of allowing the building or the member to be exposed to the theoretical ultimate moment, or the nominal moment as we called it, they calculate what they call the ultimate moment capacity and use that in their equations. All right, now, obviously, tell me, would you want this ultimate moment to be less or higher than the theoretical moment? Yeah, absolutely. You want it to be lower. So take a look at the very bottom of this page. When we calculate the nominal moment, as we did, Jacqueline just said 225.27 foot kips. We calculate that, and then we multiply it by a what we call a strength reduction factor. Strength reduction factor. All right, so we reduce it, and by doing so, we are introducing some level of safety, some factor of safety. So this ultimate, or the strength reduction factor, is less than 1, and we use the phi, the letter phi, to identify it. And sometimes we refer to it as the phi factor for obvious reasons. Now, you may ask, Is the phi factor always 0.9? No, it is not. It is 0.9 if the element that we're looking at is a beam. All right. Now here, this slide shows uh, this slide shows some of the things that I just described to you. However, what I need to do is bring to your attention the bottom, this very bottom line, the very last line. It says phi varies from 0.9 for beams to 0.65 for columns. All right? So the phi factor varies, and this is all dictated by the design code. And if it is a beam, it's 0.9. But if it's a column, it's 0.65. It's a higher reduction because columns are much more critical elements than beams are. All right? And I believe there it is. The next slide, slide number 31, here I've given you the phi factor for various elements. And sometimes, guys, it could just be this question. What is the phi factor for uh, for a for bearing on concrete? And again, once again, if you know what they're talking about, you would know where to look it up very quickly. All right? So just tag this page. Sometimes this is the question itself, or this is part of the problem that you have to solve. Ultimate moment capacity here is just a summary in words, summary of what I have already discussed with you. The only thing I want you to look at is at the bottom of this page. In that box, I am telling you rho. This is rho is simply is called the steel ratio. It is the ratio or the amount of steel that you have in the section compared to the overall dimension of the concrete. So here, rho is equal to A sub S, the total area of steel, divided by B times D. Remember, B is the width. D, pay very close attention, D is the distance from the compression side only to where the steel is. All right? We're going to skip this page. This is a problem. This is very important. It reviews some of the concepts that I presented to you, but also it introduces you to loads and codes. Loads, actually, the concept of loads, definitely you need to be familiar with it if you take the structures exam in the afternoon. But to some degree, and I will show you to some level, you need to be familiar with it for the morning exam as well. All right? So they give you a beam. This is actually pretty close to the kinds of problems you might see. The span length from support to support is 30 feet, and it carries a live load of 418.5 live load of 418.5 pounds per linear foot. Make a note of it. Pounds per linear foot this is. All right? Now, is the strength adequate? All right. ACI, this is the load equation. In this case, we need to use the load equation because we are considering live load and dead load. Those of you who are not familiar with this concept, I will tell you very quickly. There are two loads that are applied to a structural element. One is live load, which is transient. The building that you work in, for example, uh, when the people who work in it, when they are there, it's a limited time. And when they leave, they're no longer, the building is not subjected to those loads. So that's live load. Uh, Dead load, however, is the load that's sustained throughout the life of the structure. And definitely uh, one big part of a dead load is the materials themselves, the structural materials themselves. So here, the equation is 1.2 times dead load plus 1.6 times live load. These are load factors, 1.2 and 1.6. Think about it. What we're doing, this is really adding some safety level. Um, when you calculate the actual dead load and multiply it by 1.2, what you're really doing are you're adding 20% to the actual dead load. With the live load, when you multiply by 1.6, you're adding 60% more to the actual live load. We have a higher load factor for live loads because they are less predictable than dead loads are. Let's move on. Here is, I want you to follow this calculation, and I will tell you this is a comprehensive problem, what we're solving right now. On the test, however, every step, each step that I'm showing you could be a problem by itself. All right? So they say the reinforcing bar is, there are three number 8s. All right? And then the yield of steel is 40,000 psi. Compressive strength of the concrete is 4,000 psi, and its normal weight. And these are the dimensions of the cross-section. Please make a note that B is the width, D is what we've talked about, the depth from compression side to where the steel is, and then what they say T is 19 inches, but that is the total depth. Sometimes they use that TH, whatever they call it, it doesn't matter. That is the total depth. All right, now let's calculate the dead load of the beam. Here, I've done something that may confuse you, but please pay attention because I'm going to tell you, write this down. These numbers, 0.833 and 1.5833, those, guys, those are the dimensions of the cross-section in feet. All right? There it is. B is 10 inches. T is 19. If you multiply those by 12, these are the numbers that you get. And we're calculating the entire cross-section. In other words, we are using what we call T, or the overall depth. Why? Because we want to know exactly how much concrete we have in this section. Why? Because we're calculating the dead load of the beam. How much does this concrete beam weigh? All right? So the dimensions, again, in terms of feet, we're multiplying it by 150. Who can remember why 150? We talked about this earlier in this presentation. All right? Remember when I said normal weight concrete weighs somewhere between 145 PCF, pounds per cubic feet? Somewhere between 140 and 150 or 155. Here, we're using 150. Now, you may ask, on the test, what should we use? Well, if you use the answer, the tolerance of the answer will be such that if you use anywhere from 140 to 150, you would get their target value. All right? So in this case, we multiply that, and you get the dead load of the beam is 198 pounds per linear foot, and the live load was given to be 418 pounds per linear foot. That actually was given. All right. We calculate the moment at the midspan, WL squared over 8. Those of you who are structural engineers, you recognize this, and those of you who are not, you could look that up in the steel design manual, or yes, I said steel design manual because the moment diagram would be the same no matter what the material. Or you can use the principles that I showed you to draw the moment diagram and get that. All right? So in this case, you find the design load. We took the dead load multiplied by 1.2, and we took the live load multiplied by 1.6. I introduced those load factors to you in the previous slide. And there it is. M required is 113 foot kips. All right? So this beam is safe. And then in the very bottom here, it says the capacity is higher than the load. The moment capacity is higher than the actual moment, so it is safe. It's okay. There are some other things that have been calculated here. You can look at it and prove to yourself that you can do that problem. I want to continue. These are other load equations in the ACI, American Concrete Institute. And look, guys, any of these equations could be on the test. Now, don't get too upset. These are not difficult problems. All you have to do is take the values that they give you for different types of loads. For example, D is a different kind of load. F is a different kind of load. And what they do, they will give you the values for some of these, and then they say, what is the design load? Well, keep this page handy, and we're going to go forward. This is some other equations. And here on page 40, I have defined every one of those variables, what U stands for, T, L, or F. All right? So LR, for example, and so on. S is a snow load, which, we have to be worried about at the moment, no matter where you are in the nation. But anyway, what you do, they will give you some values for some of these things that are in these equations, and some of them. Now, here's a question that I always get asked. What if they don't give you the value for one of these? Well, consider it 0, all right? And then you substitute in various equations, and you get the answer. I have some good examples that I will show you when we get to the steel part of the presentation. We don't have a whole lot of time left, but problem number 5. Problem number 5, I need for you to do this one if you're taking the structures in the afternoon. Otherwise, forget it. All right? So, problem number 5, don't worry if you are not taking the structures in the afternoon. One-way slabs, specifically, they do indicate one-way slabs to be on the test, but they can't really give you a whole lot about it. However, this is something that you should worry about when it comes to one-way slabs. Tag this page, all right? They will ask you what is they will give you some dimensions and what is the shrinkage reinforcement, minimum reinforcement for shrinkage in a slab. And A sub S is that minimum steel. All right? So look at it. The steel that they give you, does it have a F sub Y yield stress less than 60 or equal to 60? And just use these dimensions. All right? And the maximum spacing is 5 times the thickness of the slab, or 18 inches. Tag this page. Basically, the one-way slabs are designed like this. They are designed like beams, but what we do is we design them like strips, 12-inch wide strips of beams. All right, and then we'll put them together. Guys, this is really important. Sometimes, and I want everybody to please pay attention, many times on the test, both in the morning or in the afternoon, but mostly in the morning, they give you a problem that has to do with structural design, they give you no numbers at all, no dimensions. They just give you a sketch. All right? And many people, unless they are structural engineers, they have difficulty with that. All right? For example, in this case, you see this, the T section, or this is a slab here. When they give you that, and they show you, you see these dotted lines, these are the location of reinforcing steel. And absolutely no dimensions whatsoever, but they give you these locations of the reinforcing bars, and they ask you which one is correct. What they're asking you really is to see if you recognize where you need to have the reinforcing bars. And I've already told you that. Where do we need it? Absolutely correct. On the tension side, all right? Wherever the steel, wherever the beam is in tension, that's where you need the steel reinforcement located. All right? So what these problems that they give you, they say, well, where should the steel be, or which one is correct? This is what you need to do. You need to identify where the beam is in tension. And sometimes the tension side of the beam can be on top, not bottom. All right? So, for example, in a problem like this, remember what I told you? Negative moments. Negative moments cause the beam to deflect like this. All right? Which means tension on top. So, wherever the beam is exposed to negative moments, tension occurs on the top. So that's why you have reinforcing bars where the tension, when the tension happens, and when the moment is negative. All right. Everywhere else, the location where moments are positive, like in this area, that yellow area, that's positive. So where's the beam in tension? In the bottom. All right. So that's where you need it. Let me give you another example of these kinds, because this is really important for the morning exam. Don't think this problems they will give you are all going to be very complicated. What about a cantilever beam? Remember, a cantilever beam is a beam that is fixed at one end like this and free at the other end. Well, think about it. How does a cantilever beam deflect? It would deflect like so. Tension on top, compression on the bottom. So if you have a cantilever beam, the reinforcing bars that you need will be top, not bottom. Now, there is another, before we move on, let me give you one more. This is also a favorite of problems on the test. They give you a wall. It could be a retaining wall with some soil at one side, or it could be water. And then they give you steel. They show you the steel on the left side or the right side. And then they ask you which one is correct. Guys, problems like that, okay, this is a vertical cantilever, all right? So every time you see this, take a look at it, and you need to identify. Yeah, Adam is asking me, is beam and moment diagram, or the shear and moment diagram, supplied for this type of equations, for these types of questions? Sometimes they are, sometimes they aren't. All right, so sometimes they are, sometimes they aren't. In the case, these last two examples with the cantilever beam and the vertical wall, the retaining wall, they don't necessarily give you a moment diagram, but sometimes they do. So if they give you the moment diagram, decide where it's positive, where it's negative, and then decide where the steel goes. Otherwise, you just have to estimate the loading. They will give you the loading, so you need to identify the loading, what kind of deflection it would cause. All right? Now, the next slide, this is the steel design manual, which I referred to last Thursday. What I have here, the next few slides, and there are several slides, I walk you through this book. I'm not going to tell you or talk about each page. I will flip through it, and you can go back, especially those of you who are taking the structures exam in the afternoon. You need to spend some time, refresh your memory on how this works. But for the rest of you, I have, and these, by the way, these tell you each page, each section, what those numbers are within each page. And you can, I did not really intend to spend much time on each of these pages. You can do that on your own, and this tells you exactly what each item is on each page. What I want to spend the last few minutes on, however, is the application of these loads. These load combinations, they do show up on the test, all right? And you need to have a good understanding of those. Very similar to the equations that we covered a few minutes ago, but those were from ACI, American Concrete Institute. This is from AISC, American Institute of Steel Construction, but you see the word ASCE. That is because ASCE 7, that is the number of the publication that controls the design loads. All right? So how do we use this? Again, this is the nomenclature. It tells you what each one of those variables are. But these are simple problems. This is a very typical problem. Everybody, please help me with it. Analysis of a building column indicates that the following loads are present. D is 100 kips. L is 150 kips. LR is 50 kips. These are the three numbers they give you. Determine the loads for which this column must be designed according to the ASCE 7 load combinations. Guys, I don't care if you have never designed anything or not looked at these equations since you left college because you're specializing in some other area other than structures. However, let me show you how this works. Remember the series of equations I just showed you 3 slides ago? Well, what you need to do is take those values that they do give you and find those letters. They gave you a value for D, for L, and LR. So substitute and plug in those values in every equation and every time you see those particular variables. All right? Now, some of these, they didn't give you. For example, in this equation down here, we used 0 because this was not given. That was W, all right? The W was not given, so we used 0. This one was not given, so we used 0. So plug in 0 for those things that they didn't give you. Now, how does this work? Once you calculate all of, this is just plug in numbers, calculate all of these, and the one that controls is the largest. Just compare the results, and 385 out of the 4 or 5 possible values, that is the controlling load, and that's all they're asking you to do, guys. All right? Now, here is another sample. This is the load combination. Joseph says, should we have a copy of ASCE 7? If you're a structural engineer, if you're familiar with it, certainly do it. If not, what I have in the handout should be enough. Just learn how to use these things that I have in the handout. All right, here the loads are given in terms of moments. MD, MLR. All right? And these are the 4 choices. Once again, substitute the values that are given and put 0 for the things that you don't have. Here, instead of loads, we have moments. And in this case, I think the answer is 58.8. Check that, Helen. Make sure that I'm correct. I think that's correct. There, 58.8. All right. Now, this is the last problem that I want to cover for you, and this goes back to the idea of section modulus. Do you remember I mentioned the term section modulus last Thursday? Okay. Well, I gave you an equation for it, and I did an example problem, and I said we will visit this when I cover design. We are there. This is it. All right? So it's very common when we design steel members, elements, we use the concept of, especially for flexure, when we design beams, we design based on section modulus. In this case, section modulus is down here, and for the given parameters, we calculate the section modulus, and we go to the steel design manual to find the section. In this case, they say the lightest W section. W refers to, it looks like an I beam. It looks like an I. So W section is the configuration of the beam. And it says the lightest because steel is, we buy steel by its weight. So we choose the lightest for economical purposes. All right? And then they say, please choose the lightest W section that resists a load of 710 foot keps or kep foot. All right? The other thing we need to know is the yield strength of the steel. In other words, what type of steel are we using? And they will give you that. In this case, 50 KSI. So here's how it works. The yield stress is 50 KSI. Calculate the section modulus. The section modulus in this case is M sub U, ultimate moment, divided by phi, which is a factor, times Fy. Now, phi B applies to LRFD, which is the load resistance factor design. Don't get too excited about that. That's a probabilistic method. If for the morning exam, that's really is not a big issue. Just follow the solution here. So we substitute the moment. That's 12. This is a conversion factor. Phi for beams is 0.9. 50 KSI is given. So the section modulus required is 189.3. I will take two more, about a minute or two more minutes, and we will be finished with this. So once you have the section modulus, then we can go to, I'm going to go to the next page. You go to these tables. This is in section 3 of the Steel Design Manual. And basically, this is the column, Z sub X. That's the section modulus. That's by the way, that's the plastic section modulus used in LRFD. All right? So that's the plastic section modulus. And this table here, that's what we need. And I have made it larger here so you can see. Basically, this is what we do. We're going to come down here and find the Z value that is at least what we calculated. You calculated 189.3. Does everybody follow? You need a section. You need to choose a section that has at least 189 inch cube section modulus. So theoretically, any section that has a number in this column, section modulus larger than 189, would satisfy the requirement. However, we are looking for the lightest section. And the lightest section is the one in the family that is in bold. And that's why we chose 24 by 76. All right? And so the answer here will be W24 by 76. For the purists among you, you may say, well, what about W14 by 109? Well, yes, in terms of section modulus, that would satisfy. That's larger than 189. But you know the second number here, when we say W14 by 109, that 109 indicates the weight. That indicates the weight of the beam per linear foot. All right? So we choose W24 by 76 because 76 is much lighter than the 109. That's 76 pounds per linear foot. All right? And the first number, by the way, 24, is the depth of the steel section. So in this case, the lightest would be W24 by 76. This last problem. It's very similar to that previous problem. This is very similar to the previous problem, except that the steel that we use is 36 KSI rather than 50. The same process. Guys, I'm going to stop at this time. I hope that you have benefited from this section. Study problems that are similar to what I presented to you, but I can tell you many of the problems you'll get will be simple, and some of them will not have any dimensions, and they will be checking and testing concepts, the concepts that I presented to you. Especially, it's very common they give you the location of the steel, and just find out what section of the concrete is in tension, and that's where you need the steel. Have a great Wednesday. I will be back with you on Thursday, and we'll cover construction materials.